Today we're going to be talking about nodal analysis, and this is a big important tool that you guys can use to analyze most circuits. I would encourage you not to use it as a crutch to analyze all circuits, because there are times where other circuit analysis techniques like KVL, KCL, Ohm's law, and all that kind of stuff will be more appropriate, but some of you are not going to listen to me, and you're just going to do this for everything. Or more likely, actually, once we learn mesh on Monday, you're just going to try to throw that at everything. So, nodal analysis is a technique where we just use multiple applications of Kirchhoff's current law in order to solve for all of the voltages in a system. And now it's just, nope, I put too many. And so we are going to learn how to apply nodal analysis by, I'm just going to give you guys an example problem, and then we're going to run through the steps and kind of develop an algorithm or a step-by-step process by which to solve circuits. So I'm going to be very upfront about this. It is an involved process, and the steps that I'm telling you to do, I'm telling you to do them in a particular order so that the equations that are very easy to forget to come up with are first, so that you will get in the habit of looking for those relationships first, and then the real brunt of the nodal analysis will come at the end. So when you have a question about a homework problem involving nodal analysis, the first thing I'm going to ask you is, did you follow my steps? And if you didn't, I'm going to make you start from scratch and follow my steps in my order. So I will browbeat you into doing it my way, whether you like it or not. Okay. So let's begin with the following circuit. Okay. So let's say that we have a 5 amp current source like so, a 10 ohm resistor, an 8 ohm resistor. Let's put a dependent current source here. I'll have the current flowing out. I'll sort out what that's going to be in just a moment. Let's have a 20 ohm resistor here. And I'm going to make this voltage Vx so that this source will be supplying 1.2 Vx of current flowing from left to right. Okay, so this is just something I completely and utterly made up. Okay, so we have this circuit. I want you guys to notice none of the resistors are connected in series or parallel. So there is no amount of, or there's no opportunity to do any simplification using resistor combination techniques. We do have two current sources, but they are not connected in parallel, so we can't simplify anything by doing source combinations. Notice that we only have a single independent source, so we can't simplify anything by doing superposition. So in a circuit like this, where all other circuit analysis techniques have failed us or exhausted us, we can apply nodal analysis. So our first step is going to be simply identifying our nodes. So I'm going to do this the way that I have always done it in this class. We've done it multiple times at this point. I'm just going to use different colors to identify all of our different nodes. And so we can see that we're going to have 4 nodes in total, 3 nodes along the top, and 1 larger node along the bottom, like so. Our second step is going to be to choose a reference or ground node. Okay. So what I mean by this specifically is that we are just going to simply assign one of these 4 nodes to be the reference point for our entire circuit. And we typically call that reference point ground, where ground represents a 0 electric potential. So just like we might use the ground, literally the Earth's ground, as a reference for calculating gravitational potential energy, so how much potential energy this stylus has with respect to the ground, we do the exact same thing for electrical potential energy in a system when we're choosing to use nodal analysis. So realistically, any node can be chosen as your reference node. However, there are some best practices. Okay? So this circuit contains only current sources, and that is by choice right now. Okay, we'll figure out what happens when we introduce voltage sources a little bit later on in this lecture. So whenever we have a circuit where we only have current sources, typically speaking, I tend to choose my ground node to be at the node that is touching the most amount of circuit elements. So that top left node is only touching 2 circuit elements. The top right node is only touching 2 circuit elements. The green node is touching 3 circuit elements. And the bottom blue node is also touching 3 circuit elements. So for me personally, I would probably choose either the green node or the blue node, but any of them will work. So what's your preference? The blue. So choosing the bottommost node is a fairly standard default choice, but technically speaking, things will work regardless of which node we choose as our reference. Okay. So now, our third step is going to be to assign nodal voltages, and I'll talk about what that means in a moment, to all non-reference nodes. So effectively, every node that isn't ground will have some voltage associated with it. So if I were to call this node on the top left node A, then I would choose to call my nodal voltage at node A VA. Similarly, I could have a nodal voltage here at the green node VB and a nodal voltage here at the pink node as VC. So let me explain what these nodal voltages represent. This is just a modified double subscript notation. And I know you're saying to yourself, well, hey, when you talked about double subscript notation on the second day of class, there were 2 subscripts. How can we have double subscript notation when there's only 1 subscript? So what we're really doing here is we're saying that node A is the positive polarity terminal for voltage VA, and ground is the negative polarity terminal. So ground will always be our negative polarity terminal voltage of the voltage for all of our nodal voltages. So really, VA is just the exact same thing as the voltage drop across this current source, because the current source is between the red node and the blue node. So the positive polarity terminal is at node A, and the negative polarity terminal is at ground. VC is just the voltage drop across this 20 ohm resistor, because the positive polarity terminal is at node C and the negative polarity terminal is at ground. VB is just the same thing as the voltage drop across this 8 ohm resistor, because the positive polarity terminal is at node B and the negative polarity terminal is at ground. So that's all a nodal voltage is. It's a voltage measured from the node you're interested in with respect to ground, our arbitrary 0 point in our circuit. Okay, so this has made things a bit too busy, so I'm just going to erase these things. But I hope that that concept of what a nodal voltage is fairly easy to understand. All right, So this is all of our setup work. And now we're going to start working on equations. So the first equation that I want us to write, and I'm going to call this step 4. We are going to express all controlling variables in terms of the nodal voltages. So what I mean by a controlling variable is a quantity, either a current or a voltage, that controls a dependent source. So we have a dependent source that says the current flowing in that top right branch is 1.2 times Vx. That current source is controlled by the voltage Vx, which is here. So all we're going to do is try to express that voltage Vx in terms of our nodal voltages. Anytime we have a voltage in a nodal analysis problem, it is always going to be simply the node that is tied to the positive polarity terminal minus the node that is tied to the negative polarity terminal. So in this case, our expression would simply be Vx is going to be equal to Vb minus 0, because our ground or reference node is always considered 0. So Vx and Vb represent the exact same thing. So just to recap, whatever node is at the positive polarity terminal minus whatever node or nodal voltage is at the negative polarity terminal is how we're going to define any voltage that we're interested in that effectively just isn't a nodal voltage itself. Okay. Any questions about that? So what if I had a current? So let's say, just for the sake of argument, that there was a different current source in here that was controlled by this current Ix. How would we express the current Ix in terms of our nodal voltages? Anybody have any thoughts? Sorry, what was that? So you said Vb minus Ix. So let me ask you a question here. Vb is a voltage, right? What are the units of voltage? Ix is a current. What are the units of current? Amps. So how can I subtract amps from voltage? The units don't make sense.
You would have taken the actual voltage minus Ix times 8, or you can do voltage divided by 8 times Ix.
So the voltage divided by 8 is Ix, according to Ohm's law, which is all we should really be doing, right? So we know that the voltage drop across the 8 ohm resistor in terms of our nodal voltages is just Vb minus 0. Apply Ohm's law, voltage divided by resistance is equal to current, right? So we could say, whenever we had a current, that Ix would just be Vb minus 0 over 8 ohms. So this part can be a little bit confusing. So I want to help you guys think about things. So an easy, quick and dirty way to remember how to express any current in a nodal analysis system is it's the nodal voltage where the current starts minus the nodal voltage the current is flowing towards divided by the resistance 100% of the time. Where it starts minus where it ends over resistor. Okay, so on to step number 5. So for step number 5, we are going to apply Kirchhoff's current law at each non-reference node. Okay. So we have 3 different nodes that are not our reference nodes. So we'll be applying Kirchhoff's current law 3 times, once at node A, once at node B, and once at node C. So I'm just going to make a quick note down here. KCL at node A. And what we're going to do is we are going to simply sum the currents that are leaving our node and add them together and set it equal to 0. Okay. So I can see that there are 2 currents that are leaving node A. So I have the current provided by my current source. Notice that my 5 amps is up and the current that I'm interested in is in the opposite direction. So I'm going to start by saying I have negative 5 amps. Now I'm going to deal with this current flowing to the right through my 10 ohm resistor. So using the method that I just talked to you guys about a minute ago about how we defined IX, how would we define that current flowing to the right through the 10 ohm resistor in terms of our nodal voltages? So VA minus VB over 10 ohms, because the current starts at node A, flows towards node B, and there's a 10 ohm resistor in the way. So we will have plus VA minus VB over 10 ohms. Those are the only 2 currents leaving node A, so we're done with this equation. Now we can do KCL at node B. So that will be this current flowing to the left through the 10 ohm resistor, this current flowing down through the 8 ohm resistor, and this current flowing to the right through the current source. So let's start with the current flowing to the left through the 10 ohm resistor. What should that be in terms of our nodal voltages? VB minus VA over 10, absolutely. What about the current flowing down through the 8 ohm resistor in terms of our nodal voltages? Yep, so VB over 8 ohms, absolutely. Somebody that isn't Ashton, because she seems to be getting this, tell me how we would do the current flowing to the right through the dependent current source. It would not. It is a little different. So it's a current source. So how did we handle the current source in our first KCL equation? We just wrote the current and then made sure that since the direction was in the opposite, we put a negative sign. This one is in the same direction, so we just add the current, right? Because Kirchhoff's current law is just adding current, so why do we need to make it any more difficult than using the current they tell us? We don't. So it'll just be plus 1.2 Vx, and we'll set this equal to 0. Yes?
Why can't we make the 5 amp current source?
So, fantastic question. So when I'm applying Kirchhoff's current law and I'm doing nodal analysis, I always sum all of the currents leaving a node and set them equal to 0. So the current leaving VA is this guy direction down. This 5 amp source is pushing current up. Since this arrow is in the opposite direction of the current source, I need to have a negative sign to tell me how much current is flowing down. So this goes back to what we talked about on our second day of class when we were talking about how currents are defined and all of that kind of stuff, right? So to fully define a current, we need both a magnitude and a direction, okay? So we have that current source over there on the left. Its magnitude is 5 amps and its direction is up. So if I want to know the current that is flowing down through that branch, because it's in the opposite direction, I have to add a negative sign to the magnitude. When we're looking at the 1.2 VX source, the green arrow, this is the current that we're trying to express. It's in the same direction as the arrow on the current source. So we give it a positive sign because we didn't need to change the direction. All right, so we've got that equation. And then lastly, we're going to have KCL at node C. So that is going to be this current plus this current. So I want you to tell me what the current flowing to the left through that current source should be. Negative 1.2 VX. Absolutely right. The arrows are in the opposite direction, so we have to add a negative sign. What would the current flowing down through the 20 ohm resistor be? VC minus 0, so VC over 20. Set this equal to 0. So let's count things up here, right? So here we have one equation. Here we have a second equation. Here is a third equation. And here is a fourth equation. So we have 4 equations and we have 4 unknowns. Our nodal voltages VA, VB, and VC, as well as our controlling variable VX. So if you guys have one of these discontinued Casio 991s, you're good to go because it can actually solve 4 equations and 4 unknowns. But the overwhelming majority of us don't have one of these because they have been discontinued. So we're going to have to make a simple substitution. Well, we know that anywhere we see VX, we could just replace it with VB. So I could just sub in VB right here, and now I have a 3 equation, 3 unknown system that I can solve using my calculator. So I'm going to do just that. Let me pull up my calculator menu thingy. So let's do the Casio 115 because we used the TI the other day when we solved the system. And let me get that system of equations on the same screen so that I don't have to go back and forth 100 times. Okay. All right, so for these Casios, the first thing I need to do is get it into my equation solving thing. So I just press the mode button and now I hit option 5 for equations. This is going to be a 3 equation, 3 unknown system. So I'm going to press option 2. And now I'm just going to put stuff in. Okay, so all I'm doing is I'm putting the coefficients in for my variables in the A, B, and C column. And then there's a D column off to the right that we can't presently see. And that's where we're going to put in our constant values. Okay, so what would the coefficient of VA in this first equation be? 1/10. Okay, so I'm just going to do 1 over 10 and hit equals. And then it'll move on to B. So what's the coefficient for VB? Negative 1/10. So negative 1/10, hit equal. What's the coefficient for VC? 0. So 0, hit equal. And then we're going to move our constant term to the right-hand side of the equal sign. So negative 5 moved over to the right-hand side of the equal sign is going to look like plus 5. So I'm just going to have 5 right here. In my second equation, what is my coefficient for VB? Or excuse me, VA? Negative 1/10. My coefficient for VB is going to be what? 1/10 plus 1/8 plus 1.2. right? And luckily for us, our calculators are way smarter than I am. So I can literally just put in 1/10 plus 1/8 plus 1.2, and it'll take that and give it the actual correct number. So 1/10 plus 1/8 plus 1.2. My coefficient, my coefficient for VC is once again 0. My constant term is 0. And now I'm at my KCL equation for node C, where, oh, and I should have replaced this Vx with Vb as well. My apologies. So our coefficient for VA here is 0. Our coefficient for VB is negative 1.2. Our coefficient for VC is positive 1/20. Our constant term is 0. And now I press enter again, and it solves things for me. So it's telling me that VA is 2850 over 53. So let me just put down here. Step number 6, solve the system of equations. So we found VA to be 2850 over 53. VB is 200 over 53. And lastly, VC is 4,800 over 53. So let me start by asking, if you guys put this into your system solvers in your calculator, did you get similar results? Yeah, good. Okay, so we all got the same results, and we all either did it equally correctly or equally incorrectly. But I think we did everything correctly. So let's talk about these results here, right? So just erasing some of this extraneous stuff that we no longer need since we've solved our system. So I can use those results to determine any voltage, current, or power in this system that I could possibly be interested in, right? So for example, if I had this circuit and I were asked, what is the power absorbed by the 5-amp source, how could I get that now that I know my nodal voltage? Okay. So if we want the power absorbed by our 5-amp source, that means we need the current flowing into the positive polarity terminal of some voltage, right? So I could call this voltage plus minus, so this would be V5 amps, right? I put the positive polarity terminal on bottom so that the current is flowing into the positive polarity terminal, out the negative polarity terminal, specifically because I'm looking for absorbed power. So we know that power should just be the current flowing through the 5-amp source times the voltage drop across our 5-amp source. Well, what's the current flowing through our 5-amp source? 5 amps, because it's a 5-amp source. What's our voltage going to be? So the positive polarity terminal is at ground. So I'm going to do 0 minus, and then the negative polarity terminal is at VA. So just 0 minus whatever VA happened to be from the results of our solving our system, right? Which, scrolling back down here, was 2850 over 53. So we would have 5 times 2850 over 53. And then I need to make whatever that is negative. So negative 1,000, there's gonna be 14,250 over 53. And our answer would be in watts because we're looking at power, right? If I wanted the power supplied by the dependent source, what would I need to do? So for power supplied, I want current flowing into the positive polarity terminal or the negative polarity terminal. Negative polarity terminal. Okay. So I could call this voltage V dependent, and I put the negative polarity terminal on the left so that the current would be flowing into the negative polarity terminal such that I times V just gives me my supplied power. So my current is just 1.2 Vx, where we know that Vx is Vb. So we would have 1.2 times Vb, which was 200 over 53, if memory serves me correctly. Let me scroll down here to make sure. Yep. What's my voltage drop B dependent going to be in terms of my nodal voltages? You were correct. Say it louder. Exactly right. Vc minus Vb, because the positive polarity terminal is at node C and the negative polarity terminal is at node B. So it is absolutely just Vc minus Vb. So that would be 4,800 over 53, and that should be in volts. Actually, let me back this out really quickly. So this 1.2 right here is in amps per volt because that is a voltage controlled current source. If I'm going to use the units, I should use them consistently. Minus 200 over 53 volts. So if we look at things, we're going to wind up having amps times volts, which is exactly what we would expect. So if I toss this into my calculator, 1.2 times 200 over 53 times 4,800. Actually, I'm going to be lazy and just do 4,600 over 53 because I can do that math in my head. I wound up getting 393.022 watts. Okay. So effectively, once we find our nodal voltages, we can find any other quantity in our circuit within one step. Okay. All right, so as an exercise for you guys, I'm going to pop over to the web work and we're going to look at one of those homework problems that I told you don't worry about until we learn nodal analysis. Now that we know it, let's see if we can use it. Okay. So we were looking at homework 5. And if I'm remembering correctly, we were looking at problem 3. Actually, so it looks like all of these have voltage sources. So we need to figure out how to take into account what happens when we have a voltage source. So we'll circle back around and knock one of these out towards the end, okay? So whenever we have voltage sources present, it actually messes things up a little bit. It's going to seem annoying at first, but as we practice, we'll actually find out that having voltage sources in a system when we're applying nodal analysis is a good thing because it means that some of our unknown quantities are known. Okay. So let's say that we have an 8-volt source here. a 15 ohm resistor. Let's make this a voltage source as well. So I'm going to call this 3ix. I'm going to put another resistor down here. Let's make this just a 10 ohm or something like that. Let's make this guy up here a 20. Let's make this 2 amps. And let's make this 5 ohm resistor over here. So we've got a circuit. It's starting to get kind of big and ugly, but that's okay. We've got 2 voltage sources and a current source. I need to define my current IX. So let's say that the current IX is the current flowing through the 15 ohm resistor from left to right. So I'm going to modify my procedure slightly. So I'm going to wind up adding a couple of steps. So let's start with step number 1, which is going to be the same thing as before. We're simply going to identify our nodes. So we've got this guy on the top left, this guy here, this guy on the top right, this guy down here, and then this guy down here. So we've identified our nodes. Our next step will be to choose a reference node. So whenever we have voltage sources present, typically speaking, I would choose the node that touches the most number of voltage sources possible, okay? And you'll see why that is in a couple of minutes. So our red node touches 1 voltage source on the top, our blue node touches 1 voltage source on the bottom. That kind of blue-green node in the top middle touches 1 voltage source on the top, and our green node on the bottom touches a voltage source as well. So all 4 of those nodes are equally as good options. Because I want to illustrate the point, I'm going to choose the green node on the bottom right to be our reference, which is probably the one most of you guys would have picked anyway. So now we're going to assign our nodal voltages. So I'm just going to go VA here in the top left, VB here in the top middle, VC here in the top right, VD here in the bottom left. Now we are going to keep our same step number 4. And we are going to express our controlling variables in terms of our nodal voltages. So our only controlling variable in this system is our current Ix. So what should my equation for Ix be? Say it louder, somebody. You're all whispering. I'm old and deaf. Listen to way too much metal in my youth. Exactly right. VA minus VB over 15 ohms. So we're going to have a new step 5. But I'm going to skip it. We're going to have a new step 6, but I'm going to skip that as well, so that when we perform our nodal analysis or KCL at node A, we will see why we need these 2 other steps, okay? So this is the space for step 5. I'm intentionally leaving it blank. Here's the space for step 6. I'm intentionally leaving it blank. And we are going to drop down here to step number 7, which is just going to be apply KCL at all remaining non-reference nodes. And I'm telling you explicitly here, there is going to be a mistake when we try to apply KCL at node A. So I would encourage you to literally not write anything down just yet, okay? So when we try to apply Kirchhoff's current law at node A, what we're doing is we are adding this current flowing down plus this current flowing to the right. It's the exact same thing we've been doing every other time we applied KCL. The current flowing to the right is pretty easy because it's the same thing as Vx, or excuse me, Ix. So we already know what that is. It should be VA minus VB over 15. But what's the current flowing down through the 8-volt source? How can we express that in terms of our nodal voltages? I will give $100 to the person that can do it. The reason I am so confident is because I know it literally can't be done. Okay. So there is no way for us to express the current that's flowing through a voltage source in terms of our nodal voltages. The reason being is that a voltage source has a fixed amount of voltage across its terminals, independent of how much current is flowing through it, right? So the best thing that we could do would be to call this I8, and I'm just going to put a little arrow here to indicate the direction down, right? So if we did KCL at node A, the best we could do for right now would be I8 down plus VA minus VB over 15 ohms and set that equal to 0. Again, I'm going to erase this when we fix it. So just be aware of that. Don't be pissed off when you have to go back and erase stuff. I told you not to write shit down yet, just to be clear. I'm going to do KCL at node D to get the other side of the problem, right? So if we did KCL at node D, we would be adding this current and this current together. So the current flowing through the 10 ohm resistor, once again, is very well defined. That would just be VD divided by 10 ohms. The current flowing up through the 8-volt source, we can't express it in terms of our nodal voltages. So instead, I would probably just have to call this I8 up. Okay. So that we would have I8 up plus VD over 10 ohms is equal to 0. Let me scroll and make sure that is indeed a 10 ohm resistor. Okay. So we have these two equations here, and they have each actually introduced a new unknown quantity, but those two unknown quantities are related to each other because one of them is a current flowing up and the other has the same current flowing down. So what I'm going to suggest, and this might seem a little weird, is that we just add these relationships together. So let me explain why we can do that. The relationship on the left is equal to 0. The relationship on the right is equal to 0. And I fundamentally believe with my PhD that I can figure out that 0 plus 0 is equal to 0. So there's nothing wrong with me just adding these guys together. So if I did that, I would literally just wind up with I8 down plus VA minus VB over 15 ohms plus I8 up plus VD over 10 is equal to 0. And I8 down and I8 up have to cancel each other out because they represent the exact same current flowing in opposite directions. So I'm left with just VA minus VB over 15 plus VD over 10. That is the exact same thing as if I had just drawn a circle around this voltage source and said, and added together the currents that are leaving that circle, where this circle is what we are going to call a super node, because it is a combination of two nodes that touch our voltage source. Okay. So now let's go back and modify those steps we left blank. Okay. So step number 6 is going to be apply KCL at any supernodes that do not contain the reference node. Okay. Here just really quickly. Okay. So if we had this supernode around our 8-volt source, I believe pretty firmly that we should probably have another supernode around this 3ix voltage source. Really, anytime we have a voltage source, we are going to have a supernode. Okay. So we have a supernode AD surrounding our 8-volt source, and then we have a supernode B ground surrounding our dependent voltage source. If you notice here, when I wrote step number 6, I said very explicitly to apply KCL at any supernodes that do not contain the reference node. So that means we would only apply Kirchhoff's current law to the supernode on the left. We would not apply Kirchhoff's current law to the supernode in the middle because it contains our reference, or it contains the ground node. Okay. So our equation, when we apply KCL there, would just be what we came up with earlier. VA minus VB over 15 ohms plus VD over 10 ohms is equal to 0. And I'm going to now just erase all of this stuff because we have all of that information encapsulated in our KCL supernode equation. So now let's go back and revisit step number 5. So when we performed nodal analysis on our first circuit that only had current sources, we had an equation for each of our nodes, right? So we had an equation for KCL at node A, an equation for KCL at node B, an equation for KCL at node C. Well, we effectively just handled two nodes, nodes A and D. Let me actually just put this out here. So this was KCL at supernode AD. So it seems like we're probably going to be missing an equation, right? If we have two nodes, we should have two relationships. The other relationship is having to do with the voltage source itself, okay? So step number 5 is going to be to write a voltage relationship equation for each voltage source. So we have two voltage sources, so we're going to write two voltage relationship equations, okay? So let's start with our 8-volt source. And we'll talk our way through how to write this voltage relationship equation, which we actually already know how to do. Which nodal voltage is at the positive polarity terminal of our 8-volt source? VA. Which nodal voltage is at the negative polarity terminal of our 8-volt source? So our voltage relationship equation is 8 volts is equal to VA minus VD. So it's just whatever voltage we are told we have is equal to the voltage at the positive polarity terminal minus the voltage at the negative polarity terminal, which is literally how we've been expressing voltages the whole damn time, right? So it's nothing new. It's just in a slightly different context than we saw before. So I want you guys to tell me what my voltage relationship equation for my dependent source should be. I'm helping nothing. 3Ix is equal to VB. That's it. Now, excuse me, this guy right here kind of explains why we don't need to write a Kirchhoff's current law equation for that supernode, okay? Because we already have a relationship. That KCL equation doesn't provide us with any new information at all. All right, and so now we are at the point where we could write KCL at our remaining nodes. And the only one that we don't have taken care of is just node C. So now we'll write KCL at node C, which is just this guy plus this guy plus this guy. So what's the current flowing to the left through the 20 ohm resistor? So VC minus VB over 20 ohms. What's the current flowing down through our current source? What's the current flowing down through that rightmost resistor that I can't remember? VC over 5. Set this equal to 0. Let's just check some things here. So here we have one equation for Ix, a second equation, a third equation, a fourth equation, and a fifth equation. Let's see if that makes sense. So we had 4 unknown nodal voltages, VA, VB, VC, and VD. We also had an unknown quantity Ix. We have 5 equations, 5 unknowns. We're done. Now, none of our calculators can do a 5 equation, 5 unknown system, which means we might have to use a computer algebra tool like MathCAD in order to solve this system. So I'm going to show you guys exactly how to do that. I'm going to go through this relatively quickly because I believe you all should have used MathCAD in prior classes. If you haven't, let me double check this before I tell you I did something and then it turns out I didn't do it. $221, there we go. Sorry, I teach too many classes. Right here in the introduction section of the Engineering 221 course page is instructions for downloading and installing MathCAD Prime 8.0. So you go to this website, here's the login, here's the password. There are instructions once you log into this thing that tell you what port to use and all of that kind of jazz. So at your leisure, if you don't already have MathCAD installed, go ahead and get it installed. All right. So we've got MathCAD open here. You need to use, well, I say you don't need, I'm saying you need to use the university license. Technically, that's not true. If you want to pay for your own license and squander $100 of something for something that the university gives you access to for free, you go nuts. But the solve block operation, which is what's used to solve system of equations, does require the paid license. So you will need to use the university's or your own license for this, okay? So I'm just gonna drop a solve block here into my sheet and I'm gonna make it much larger because we've got a lot of information to put into here, okay? So in this guess value area, this is kind of like what you did in your 120 series when you were writing code. You are declaring your variables, okay? So we are gonna have our 4 nodal voltages. So I'm gonna have something for VA. To do the subscript, I'm pressing Control underscore. And there are 3 different equal signs in MathCAD because they just want to confuse the hell out of you guys, okay? So this first equal sign that I have right here, which looks like a colon and then an equal, you get that by pressing, let me double check, Shift colon, okay? And so this is how we do a declaration statement for a variable. So we're saying there is a variable VA, and I am guessing that it is equal to 1 volt. Okay. We need to just start with something to let the computer know where to start from when it begins its iterative process of solving this system of equations. You could use 0 volts, you could use negative 45 volts. Generally speaking, it doesn't matter. But every now and then, you'll get a system where the guess values do matter. If you're using MathCAD to solve polynomials and stuff like that, the guess values matter very much because this can only spit out one result, and a polynomial might have multiple results, and it's just going to give you the result that is closest to the guess value that you started with. Okay. That will never be an issue in this particular class, but if you use this for your later classes, it will absolutely matter, okay? So I'm gonna do the same thing for my other few variables. So VB, it's being dumb, there we go, is equal to 1 volt. VC is equal to 1 volt. VD is equal to 1 volt. By the way, you're not required to use units with MathCAD, but I literally always do. If you're going to use units, you have to use them for literally everything, or you will get an error. So either use units all the way or don't use them at all. And then down here, I'm going to declare my current IX, and I'm going to guess that it has a value of 1 amp. Okay. So those are all of my guess values, establishing my 5 variables for my system. Now in the constraints section, we are just going to put in those 5 equations that we got by applying circuit analysis to our system, right? So I'm going to do IX, and now I'm going to do control equal. So this is a big bold-faced equal sign that you get by doing control equal. And what this equal sign means is force everything on the left-hand side of this equal sign to be equal to everything on the right-hand side of this equal sign, okay? So if we don't do a controls equal here thing, we're not making sure that all of our relationships must be satisfied as the computer solves our system of equations. So if I'm remembering correctly, this was VA minus VB divided by, was it 15 ohms? Okay. So just to show you guys something here really quickly, if we go into the symbols menu, we have a bunch of Greek letters and all of that kind of stuff. So here we could have our omega, which is used for the ohm symbol. Notice that it says capital W, comma, control plus G. So that is a keyboard shortcut. So let me back out of this really quickly. So if I do capital W and then control G, that gives me capital omega, which is interprets as the units of ohms. There is a method to that madness, okay? So just for explanation's sake, if we did lowercase w, that looks kind of like the lowercase letter omega in the Greek alphabet. Control G just converts that into Greek. So because lowercase w looks like lowercase omega, that's why capital W gives you uppercase omega. I know it's weird, but that's the reasoning behind it, okay? So capital W, then control G gives you the uppercase omega that we can use for the ohm symbol. So there's our first equation. Then we had our voltage relationship equations. So we would have 8 volts is equal to, so that's control equals, and if I'm not mistaken, that was VA minus VD. Then I have my other voltage source, which was 3 IX, right? Okay, so because I'm using units, we need to pay attention. So we had a current controlled voltage source. So what should the units on the scaling factor for the current controlled voltage source be? So it should be volts per amp, because it's taking an input of amps and converting it into a voltage. Just for reminding you guys, we talked about what those default units for those were on our second day of class when we introduced all of the different symbols for voltage sources and current sources and all of that kind of stuff. So if you aren't given it in your problem, you can always refer back to that second class's notes and know what those units should be. So I'm going to put in 3 volts per amp multiplied by IX, and this will be control equal to VB. And I believe that's my third equation, right? Then I have my KCL at supernode AD equation. So that looked like VA minus VB over 15 ohms plus VD over 10 ohms is control equal to 0. And then lastly, I had my KCL at node C equation, which was VC minus VB over, was it 5 ohms? Let me just look. Over 20, okay. Plus 2 amps and then just VC over 5. So over 20 ohms plus 2 amps. Was it? Sorry, I have the memory of a goldfish apparently. It was indeed 2 amps, great. Plus VC over 5 ohms is equal to 0. Control equal to 0. There we go. All right, so those are my 5 constraint equations. You don't necessarily have to do them all like this, so it wouldn't have hurt anything if I moved this guy over here and this guy over here to like combine, you know, make it take up less room. But having your equations overlap a little bit can cause MathCAD to freak out. So definitely don't do that. I'm okay with killing digital trees and just making this take up the amount of space to put everything on on its own line. All right, So in our last bit, we have the solver section, okay? So this first thing that I'm going to do is technically optional. However, it is an extraordinarily good practice, so you should always do it. It isn't required for it to solve your system, but you should always do it, okay? So what I'm going to do is I'm going to put in a matrix. I'm going to do a 5x1 matrix because I have 5 variables. So I'm just making a 1 column effectively. And in this column, I'm going to put in those 5 variables. So that would be VA, VB, VC, VD, and IX. I am now doing shift colon to give me that equal sign. And now I'm going to use the command find, and I'm going to put those variables back in. So VA, comma, VB, VC, VD, and IX. And now at the end, I'm just going to use the regular good old normal equal sign, and it spits out all my values. So what me adding this matrix did is it's effectively telling the computer, hey, when you find all of these variables, store them in this array so that they can be used outside of the solve block. Okay. So this is kind of like making them a global variable so that you can manipulate them further. So let me explain what I mean by that really quickly. If we looked at our circuit diagram here, and we wanted to find the power supplied by the 8-volt source, okay, how would we do that once we've solved our system and all that kind of stuff? So we need the current that's flowing into the negative polarity terminal. What's the current that's flowing into the negative polarity terminal of our 8-volt source? IX. So it would literally just be 8 volts times IX, right? So I can go into MathCAD really quickly, and I can say P 8 volts is equal to 8 volts times IX. And it gives me that that particular source is supplying 2.286 watts of power. If I didn't have that matrix, it doesn't know what IX is. So that matrix allows us to do math outside of the solve block based on the results of our solving our system of equation. In electrical engineering, because so many of our problems are, we're effectively just doing the nodal analysis as a setup to know what things are, and then we're going to do some post-processing involving calculating powers and things like that. It's always good practice to store everything in that matrix. All right, so here's how you'll use MathCAD and all of this kind of stuff. You definitely need to have this or a similar computer algebra tool installed on your computer to do your homework. Problem 7 on the homework set that is assigned for you guys today, if I'm remembering correctly, will involve an 11 equation, 11 unknown system because the person who came up with that problem hates everyone. So doing that by hand is just never going to happen, okay? Let the computer do the work for you. So if you have a system that's a 3 equation, 3 unknown, or 4 equation, 4 unknown, where you can make a substitution, use that as practice for your calculators. Anything bigger than that, throw it in the computer. It's not worth the effort, okay? All right, so do you guys, I've talked for 75 minutes straight, effectively. Do you guys want to look at one of those homework problems applying nodal, or do you just want to do that of your own volition because that's 100% how you should be doing it? Do you want me to help? Okay, Ashton is shaking her head to help, so let's help. So let's look at just part B right here, okay? I guess technically I forgot step 8, which is just to solve the damn system, but you guys probably got that we were supposed to do it at that point. So anyway. All right, so I feel like the circuit that we were looking at had, it's like a current source over here. And then we had some resistance. And then a dependent source. Did I get that backwards? I did indeed. All right, so let me just see what my numbers are. So I1 is 1.2, I2 is negative 6.8. So 1.2 amps. This one was negative 6.8. So I'm going to put it as 6.8 amps. And I'm just going to change the direction on that current source because I don't like negative numbers. Then we had R1 is 33, R2 is 44. And then lastly, this is a 5 IY current voltage source where IY is the current flowing down through R2. So this is the circuit with my numbers, okay? So what's our first step? Identify our nodes. So there's one node. There's another node. Here is our third and final node. What's step 2? So which node do you guys want to use as your reference? Red, green, or blue? So I heard somebody say blue. So I would tend to do the green node. So since I only have one voltage source, I would probably put my reference node at the negative polarity terminal of that voltage source. You could do the blue node. You could do the red node. I'm going to choose the green node. So by choosing to put the green node as my reference, I have forced my only supernode to contain my reference node, which means I don't have to write KCL equation for the red node or the green node at all. So by choosing that particular node as the reference, I have eliminated a lot of the work involved with applying nodal analysis. Okay. So now we need to define our, actually now we need to assign our nodal voltages. So let's just call the red node VA and the blue node VB. Now we need to express our controlling variables in terms of our nodal voltages. So we only have a single controlling variable, IY. What will that be in terms of my nodal voltages? What node does it start from? Ground. So 0 minus. What node does it flow to? VB. So negative VB divided by 44. Now I need my voltage relationship equation. So what's that going to look like? Okay, so 5IY is equal to VA. Absolutely right. We could put the -0 if we wanted to, but that's not really adding anything, and I'm lazy, so I'm not going to put it there. But you're 100% correct. There's our second equation. Because our supernode, so just to be clear, this is our supernode, contains our ground. We do not need to write a Kirchhoff's current law equation for our supernode, so we get to skip step number 6, I think it is, and go straight to step number 7, where we are simply applying Kirchhoff's current law at any remaining non-reference nodes that we have, which is just node B. So we're going to be adding this current plus this current plus this current plus this current together. So what's the current flowing up through the 1.2 amp source? 1.2 amps. What's the current flowing up through the 33 ohm resistor? VB minus VA over 33 ohms. What's the current flowing up through the 44 ohm resistor? Negative IY or VB over 44. What's the current flowing up through the 6.8 amp source? Negative 6.8 amps, set it equal to 0. We now have a 3-equation, 3 unknown system that any of our calculators could solve, where our variables are VA, VB, and IY. So nodal analysis makes that so much easier than throwing superposition at that terrible circuit. Maddox, what up? So whenever I have a voltage source, I practically always choose my reference node to touch my voltage source. Okay. And the reason for that is I'm going to have a voltage relationship equation, but that also is saying that at least one of my supernodes is going to contain my reference node. If we look back at our steps here, step number 6 tells us to apply Kirchhoff's current law at any supernodes that do not contain the reference node. So if I make my reference node touch the voltage source, that means I don't have to write a KCL equation, which is work. And if I can avoid doing work, I'm going to avoid doing work. Okay. So I wouldn't have to write KCL if I had made either my red node my reference or my green node my reference. I chose to make the green node my reference so that when I write my voltage relationship equation right here, I don't just have an extra negative sign floating around. So if I only have a single voltage source in my circuit, 99 times out of 100, I will choose to put the ground at the negative polarity terminal of my voltage source. You can put it anywhere and still do the circuit analysis and come up with the same results for at least IY. The results for VA and VB would probably be different because the nodes are going to be different depending on where you choose your reference. But that IY is always going to be the same thing. And as it happens, that's what we were looking for anyway. So solve this system, homework done. I'll leave it up to you guys to take a crack at part C. Okay, so you've got 25-ish minutes left of class. So you've got an in-class assignment that contains, I think, either 2 or 3 problems. So give them a whirl and see what happens. If you got any questions about anything, please feel free to ask.